So just like when we defined what it means for two vectors to be parallel, we have a notation that we can use to concisely say that two vectors are orthogonal. So, and this is it, right? So if I want to say that two vectors x and y are orthogonal, I'll just write x and y. I'll write the two vectors with an upside down capital T in between them, so to speak, right? That's kind of what this symbol looks like. But this symbol actually has a name. It's called a perp symbol. So perp is in short for perpendicular. But anyways, that's the notation. If you want to concisely say that x and y are orthogonal, you can write this notation down instead of having to actually say it out loud, like say it in words, right? Just saves you a bit of time. Let's look at an example. So I'm going to write down two vectors, and these are actually going to be four-dimensional vectors. I'm going to call one u, and I'm going to call the other v. So -2, 3, 1, and 4, those are going to be the coordinates of the vector u. And then the vector v is going to be given by the coordinates 1, 2, 0, and -1. So let's say we have those two vectors, and let's ask the question, are they orthogonal? Well, you're not going to be able to tell by drawing them and then checking whether the angle that they form is equal to pi over 2, because you're not going to be able to draw them at all, right? It makes no sense to even speak of the angle between them, because that's strictly a 2- and 3-dimensional idea. But we can just check if their dot product is 0. That's what it means for two vectors to be orthogonal anyway, so we don't need to draw them, right? Let's just take their dot product and see what we get. So if we compute the dot product of u and v, what you're going to get, well, multiply their first coordinates. You get -2 times 1. Then multiply their second coordinates, and you get 3 times 2, multiply their third coordinates, and so on, right? So we're going to have 1 times 0, and then 4 times -1. That's what I get if I multiply each of their respective coordinates. And then if you look at what each of these products are, this is -2. 3 times 2 is going to be 6. 1 times 0 is just 0. 4 times -1 is -4. So add up all those products. -2 and +6, that adds up to +4, plus 0 plus -4. It's just going to cancel out and give us 0. So we end up getting 0 for the dot product. So that means that u and v are orthogonal. So we can conclude, therefore, that u is orthogonal to v. That's how we can use that notation to express it. And I'm going to put a box around this just because it's our conclusion. I want it to stand out, although typically I reserve that for when it's an answer to a specific question in an example, even though there was no question asked here. That's still what we were trying to determine. We're trying to determine whether or not two vectors were orthogonal. So in this case, they are. Next, we're going to speak about lines, particularly lines in R2. There's a nice way that we can use the idea of orthogonality of vectors to come up with a really convenient way to both define and also express a line in two-dimensional space. So that's what we're going to mention right now. So a line, which I'm going to call L, just so it has a name for the moment, in R2 may be defined in the following way. A line is actually a collection of points, right? It's a collection of points that all satisfy a certain condition. Now, what is that condition? Well, informally, you might be tempted to just say, well, they're all on a line, right? Or they're all collinear. But that assumes that you know what those words really mean, right? We kind of have an intuitive notion of what it means to be a straight line in R2. But what is the actual definition? That's actually maybe a little bit tougher to say, but you can say it precisely. And actually, the definitions that we've just come up with are going to allow us to do that. So here's the definition. A line L in R2 may be defined as the collection of points, and this is a typical form of a point on the line L. So it's the set of all points of this form that satisfy this condition. The vector n, which we haven't even mentioned what that is yet, is orthogonal to the geometric vector that goes from P0 to P. Well, we haven't even said what P0 is either yet. So that's another unknown thing that we still have to quantify by the end of this sentence. But if you keep reading, it just says for some fixed point P0, and we actually have labels for the coordinates of P0, and some fixed vector n, which has its own coordinates AB as well. So each of these points have two coordinates because we're talking about points in R2, right? So what is this condition, and what on earth does it have to do with a straight line? Well, remember what I said. or remember at the end of this definition, it's stated that P naught and N are fixed, right? This point P is just a placeholder that really is used to describe what the condition on a point P, or what a point on the line must satisfy. So we needed to give that point a name in order to do that. So you can think of this as a point that can vary all along the line. This could be any point on the line. But P naught and N, this point and this vector, those are fixed in the background. So let's start with those. Start with the things that are fixed. So what if I were to take a point here, and I'll just label it as P naught. I won't write down the coordinates. We can just refer to them later if we need them. Okay, and so that's what you have. You have a point P naught, and in the condition, N is orthogonal to the geometric vector from P naught to P. It looks like we're going to form a vector that goes from P naught to some point P. But in order to check whether this vector is orthogonal to this vector N, we would need to draw them so that their initial points coincide. So I'm going to draw the vector N with its initial point on P, so that we can actually think about and get an idea of what this would look like. Okay, so I'm going to just draw the vector going up like this, although in general it could be, we don't really know if it's going to point up or down or left or right, but just to stay general, we have to draw something. So let's draw it pointing in that direction. So I'm going to label that as the vector N. Okay, so now here's how this condition actually relates to a straight line, which is what we're trying to define. Then by this condition, I mean this one here. What's the only thing that we haven't drawn? We haven't drawn the point P. And as soon as we draw the point P, we'll be able to draw the vector that goes from P naught to P, which is what this notation really is here. So, well, where would we have to put P in order for this to be true? In order for this vector N to be orthogonal to the vector P naught P. Like I couldn't put the point down here, right? Because then the vector that goes from P naught to P would be going down like this. And that's not orthogonal to the vector N. Similarly, I'm not going to put the point P up here, because then the vector that goes from P naught to P is going to be this vector. But that's not orthogonal to the vector N either. They have to form a right angle. So, but maybe I could put the point P somewhere like right here, right? That would work. Or here, or here, or here, or maybe over here, or here. There's something, see all those options, they all kind of have something in common. They all lie on a line. So that's what this condition actually has to do with a straight line. All the points P that are actually going to satisfy this condition, they all lie on a line. So we're going to define the line to be the collection of all such points that satisfy this condition. Where P naught and N, they can be anything you like, but they just have to be fixed beforehand. So let's finish the drawing now. So maybe I'll put a point P right here, and then I'm going to use a ruler to finish this drawing, just because otherwise it'll just get a bit messy. So here's the vector P naught P that we've got right here. And if these are going to be orthogonal, then we'd have a right angle here. But the idea is, this P is not the only choice of point that would make this equation, I shouldn't say equation, make this statement true, right? We could have just as easily, and I'll use a ruler just for emphasis here, I could have picked this to be the point P, or I could have picked this to be the point P, or I could have picked P to be over here, over here, over here. In between there, I could have picked it here. Any of those points would have worked, right? They all would have still retained the property that this vector N and the vector that goes from P naught to P are orthogonal, right? If I replace the point P with any of the points on this line, it would work. So that's why this line ends up being determined, the one that I just extended out. So this is really the line L that you're defining. As soon as you insist that the line, first of all, you have some point that the line definitely contains, like some point P naught, and you have this vector N. That essentially this vector N points in a certain direction, and then it tells you the orientation of the line once you get to that point. You can think of it this way. Once you know the vector N and you draw it, just think of the vector N as a tree that grows straight up. If you're looking at a tree that grows straight up, you know that the ground must be totally horizontal and flat, right? If I covered up this line let me get a blank piece of paper to illustrate the idea. If I were to completely cover up the line, and all you could see was the normal vector, which I haven't actually called the normal vector yet, but that's the name we're going to give it in a moment. But if all you could see is this vector n, what is the line? Is the line going to look like that? No. You have to have the line must be, in a sense, the flat ground that the vector n grows upward from. So you know that the line has to look like this. It can't look like this. It can't look like this. It has to look like that, so that you think of the line as the flat ground and the vector n as a tree growing completely vertically. Okay, so anyways, I made a slip there, and I used the word before I actually mentioned it, but I just want to add it in at the end of this definition. So a line L is in R2 is just defined to be all the points P that satisfy this condition for some fixed point P naught and some fixed vector n, which we call the normal vector. So I'll add that in now, called the normal vector. Okay, and now what we're going to do is we're going to unpack this statement a little bit. Unpack the statement that says the vector n is orthogonal to the geometric vector that goes from P naught to P. So what does that mean? Well, let's spell it out down here. So the vector n is orthogonal to the vector that goes from P naught to P, if and only if, well, if their dot product is 0, right? That's the definition of two vectors being orthogonal. So 0 has to be the dot product of n and the vector that goes from P naught to P. Okay, well, what is the vector? We already have coordinates for n, right? The vector n has coordinates a and b. So if we want to work out this dot product, we just need to get the coordinates of the vector that goes from P naught to P. Well, we have P naught, it's right here. And we have the vector P, it's right here. So we can write the vector P naught P. Well, just take, remember how that works? Just take the x coordinate of P and subtract the x coordinate of P naught, and that will get you the x coordinate of the vector that goes from P naught to P. So just take x and subtract x naught, and you're going to get x minus x naught. Then to get the y coordinate, just take the y coordinate of P and subtract the y coordinate of P naught. So you're going to get y minus y naught. Okay, so that's this vector here. Well, now we have coordinates, so we can write out the dot product. So the vector n is, let's write it this way, AB dot product with the vector x minus x naught, y minus y naught. And then if we actually work this dot product out, multiply the first coordinates, and you're going to get a times x minus x naught plus b times y minus y naught. Okay, and this is supposed to equal 0. So actually, if we just skip all the stuff in the middle and just say that this has to equal 0, that is actually going to give you the equation of a line. Okay, so we obtain the equation of a line in R2 passing through the point P naught with normal vector n. This is just a reminder of the stuff that we already had above up here. But, well, you're just going to get a times x minus x naught plus b times y minus y naught is equal to 0. That's one way to write down the equation of a line in R2. This actually has a name. It's called point normal form. So this is called point normal form of a line. Why is it called point normal form? Well, because it gives you, if you just look at this right off the bat, if I tell you that this is the equation of a line, it tells you right away what the normal vector is. Just pick off the coefficient of x minus x naught and the coefficient of y minus y naught, these two numbers in front. That's how you can form your normal vector. And then you can also get a point on the line. Just take this value here and this value here, put them together, and you get your fixed point P naught that is on the line. Okay, so that's why it's called point normal form. Let's look at an example. In this example, we're told that the line through the point 3, negative 7. So here's your fixed point that's on the line. Think of this as your P naught. With normal vector n, which is given in coordinates as 6, 1, this is given by the equation. Well, just plug everything in, right? This point, 3, negative 7, just plug these values in for x naught and y naught. And then the normal vectors, coordinates 6 and 1, plug those in for a and b. So really what you're going to get is 6 times x minus 3 plus 1 times y minus negative 7. Right, if I just plug things in directly into that formula. Well, let's clean this up a little bit. Let's usually you won't write this as y minus negative 7 unless you're really being picky and you really want to write the equation so it fits this form exactly. But typically, for something like this, you would just write it as y plus 7. So we'd have 6 times x minus 3. And even that 1, we don't really need to write that 1 there, right? We can if we want to really emphasize that this fits the form of a line perfectly, but it's not doing anything. So typically you'll just omit that as well. So you'll write just y plus 7. So that's typically how you'll write it. Let's draw a picture. Let's draw a sketch of this line. So I'm just going to draw the Cartesian plane here. Okay. Well, what do we have to draw? Let's start with the normal vector n. It's got coordinates 6 and 1. So how about this? I'll label the 6 right here, and I'll label the 1 right there. So the normal vector is essentially like this. Hopefully this picture works out okay. It's not going to be drawn perfectly to scale, but I'm going to draw a ruler, or draw a ruler. I'm going to use a ruler just to help the picture come out a little bit better than it otherwise would, so that it makes sense in the end. Okay, so that's the normal vector. What about the point P naught, which is given up here? It's got an x coordinate of y, or pardon me, an x coordinate of 3 and a y coordinate of negative 7. Maybe I'll extend this down a little bit. So if this is 6, then we have to go a little bit bigger than that for 7, but it's going to be down here because it's negative 7. So I'll put the negative 7 down here. That should work out okay. And then the x coordinate's 3. Well, that should be halfway between 0 and 6. So let's say this is 3 here. Okay, so that'll work. Then what do we have? Well, the point 3, negative 7, that's going to be down here. So that is your P naught. Okay, so now what we're going to do is copy what we did up here. Remember, the normal vector gets drawn specifically so that it has initial point P naught. So what that means in our example is that it's going to be drawn specifically so that its initial point is down here. So let's do that. So I'm going to try my best to keep this preserved. So I do really just want to translate this vector down so that it starts at this point. Let's just out of curiosity. So what is it? This is a little bit less than 2.5 centimeters. So I'm just going to slide this down. It's not going to be a perfect sketch, and I'm going to try my best to draw about 2.5 centimeters in length. So that's still just another copy of the normal vector. Okay, and now what you're going to do is now we're going to fill in the line. Just ask yourself, where would this have to go so that this is orthogonal, right? I'm not going to draw the line like that. Because if I draw the line like that, this normal vector is not really going to be orthogonal to it. And I'm not going to draw the line like that either. Because then that angle would not be orthogonal. What I want to do is just get it just right like that. Right, and that's about as close as I can get. So this is actually your line right here. So that, and just to be as clear as possible, this is the line L. That line there. Right, so this is the normal vector. This is also just another copy of the normal vector that we originally drew. But this line coming down here that goes on forever in both directions, that's actually the line that's expressed here in point normal form. Let's expand this out and turn it into slope-intercept form, which is also a way you can write down a line, right? Let's turn it into slope-intercept form and see how our picture compares to see if this actually worked. It was kind of done not quite freehand because I had a ruler, but it wasn't that far away from being done freehand, so it's not going to be perfect, but let's see. Let's expand this out. We're going to get, and I'll just separate this because this is a separate section of work. If I expand the 6 into the brackets, I'll have 6x minus 18 plus y plus 7 equals 0. So really you have 6x. This negative 18, if you add 7 to it, really you got negative 11. So I can say I've got 6x minus 11 plus y is equal to 0. Or in other words, if I write it in slope-intercept form now by solving for the y, I'm going to get y is equal to negative 6x plus 11. So now ask yourself, does this line have a slope of negative 6? Well, negative 6 is pretty steep, and negative means it's pointing downward. Negative 6 is certainly a reasonable slope. How would you check? You'd have to pick 2 specific points and measure the slope between them and see if it works out. But this just by eyeballing it, it looks pretty good. And then also the y-intercept of positive 11, does that sound reasonable? Well, maybe not here, depending on how you look at this. But is this really a right angle? We know what probably caused that is that this wasn't quite enough to make this orthogonal. This should probably been more like that. So why didn't I draw it like that? Because it would have went right off my graph. So I had to take some liberties here a bit. So probably we should have done it more steeply like that. And then that would have brought us way up to about a y-intercept up here, which would be more reasonable for positive 11. So that's what maybe went wrong. So the picture's not perfect, but that's how you can, at least that's how you can relate the idea of drawing a line that's in point normal form versus writing it out in slope-intercept form. Okay, as we've done down here. So that's just an example of how this really isn't coming up with anything new. This is just giving you a new way to define. This is really the guts of the definition here. It gives you a new way to define a line in 2 dimensions.